Good afternoon, everyone. On behalf of the Southeast New England Program Network, welcome to our webinar titled Prioritizing Nature-Based Stormwater Projects to Maximize Community Co-Benefits in the Buttonwood Brook Watershed, brought to you by the Southeast Regional Planning and Economic Development District, Buzzards Bay Coalition, and Paradigm Environmental. My name is Leah Solway from the New England Environmental Finance Center, and I'll be managing logistics for today's program, along with Danica Belknap, SNP Network Partner with the Southeast Regional Planning and Economic Development District. Before we get started, I'd like to introduce and provide you all with a little background about the SNP Network. The SNP Network's mission is to empower communities to achieve healthy watersheds, sustainable financing, and long-term climate resilience through the management of stormwater and restoration projects. The SNP Network focuses on building local capacity by providing no-cost trainings, webinars, and technical assistance to communities in the SNP region. If you'd like to learn more, please visit our website, snpnetwork.org. And before we begin the webinar, there are a few logistics to keep in mind. First, everyone will be on mute to ensure audio quality. At the end of the webinar, there will be a Q&A session. You will be able to ask questions by typing them into the Q&A box on your Zoom control panel. We look forward to answering questions, so please type them in at any time. We have closed captions available for today's webinar. To view the closed captions, please click on the closed captions icon in your Zoom control panel. And on that note, I'll hand things over to Danica.
Thanks so much, Leah. Good afternoon, everyone. I hope everyone's having a good day. My name is Danica Belknap. I am the Environmental Planning Manager at SERPED, which is the regional planning agency that provides technical assistance to communities in Southeastern Mass. So we are a partner in the SNP Network, a technical assistance provider partner. And we were kind of the project manager on behalf of the SNP Network for this technical assistance project that came through last year to work with the Buzzards Bay Coalition to prioritize stormwater projects. So if you can go to the next slide, Leah, I'll kind of do a quick introduction of the project team here. So as I mentioned, this was a technical assistance project that was awarded through the SNP Network. And the project manager who the request came from, it was from Buzzards Bay Coalition. So Dan Goulart submitted the request looking for assistance with helping to prioritize where and what type of stormwater management projects would have the greatest impact in terms of not only improving water quality in Buttonwood Brook watershed, which he's going to talk a little bit more about in a moment, but also seeing what other types of co-benefits we could also leverage with different types of projects. So that's kind of a little background of the history of the project last year. This prioritization took place last year. Also on the project team, we had from Paradigm Environmental, Ben Bose and Khalid Alvi helped with the mapping and the modeling process for this project that you're also going to hear a little bit about. Ben Bose will be presenting today, but both are available on this call. Both were involved in the project and both are available on this webinar to answer any questions that might come through. And myself, I assisted with the site prioritization tool that we'll talk about. That was just kind of a quick intro, but I'll hand it over to Dan right now, who's going to give us an overview of Buttonwood Brook and the project.
Hey, how's everybody doing? All right, so Buttonwood Brook is a small watershed located in southeastern Massachusetts and crosses municipal boundaries between the town of Dartmouth and the city of New Bedford. Let's push ahead to the next slide. All right, that looks like an intro slide. Let's go one more. So what you saw there was a lot of the project partners, and the project partners really included the two municipalities, Buzzards Bay Coalition, a local land trust, the Dartmouth Natural Resources Trust, and a collection of scientific institutions that really helped us with a lot of the studies that went into this project. So the project is a 5-year SNP pilot watershed initiative grant funded project. You can see the funding numbers there. And in addition to the funding that came from SNAP, we also leveraged funding from a lot of different sources, a lot of different grant sources, municipal sources, ARPA funds, CPA, and really at this point in the project, we're at about $6 million plus in leveraged funds, in addition to the $1 million in grant funding and match that came in under the SNAP Pilot Watershed Initiative. So the approach to this project was really in the first couple of years, get out there and assess the watershed, understand the current conditions in the watershed, both from a water quality perspective and from a structural perspective. So a lot of water testing, a lot of walks on the brook to look at structural impairments, habitat assessments. And throughout those years, we're also doing a lot of stakeholder engagement and trying to pull local stakeholders, not just municipalities, but from the public into the project to see if we could engage them and have them be active participants in the site selection process. And now we're going into year 4 after October here. So we're actually most of the way through vetting out project sites. We've developed conceptual plans for a collection of project sites, and we're moving towards implementation in years 4 and 5. Next slide. And the project really sort of has 2 parallel goals that are tracking alongside each other. And one is to improve water quality. We've spent a lot of time in the field identifying the largest sources of pollution, both surface and groundwater sources of pollution. And we've been working with partners, engineering consultants to identify potential solutions to implement at some of the sites that were eventually selected. And we are implementing a variety of solutions, everything from green infrastructure to ecological restoration, and working with the town of Dartmouth right now on sort of a potential incentive program to bring people off of septic and onto sewer. And then we've got ongoing monitoring. And then the second objective was really to sustain that water quality over time. And to do that, we've been working with the Buzzards Bay National Estuary Program, and several other institutions to develop a nitrogen threshold report that will eventually go to EPA and Mass DEP, so we can establish a nitrogen TMDL for Apponeganset Bay that will help the town to regulate and look for ways that they can meet the nitrogen threshold and maintain healthy aquatic ecosystems that benefit everybody in the town.
Okay, so I'll talk now about, some of the work to support what Dan was doing, some modeling work to highlight pollutant sources and really help Dan pinpoint areas to look at. So next slide, please, Leah. So I'll talk a little bit about our technical modeling that we did and some of the watershed delineation. All of that was to support Dan by looking at stormwater loads, sort of unattenuated source level stormwater loads of runoff and pollutants. And we do that with EPA's OPTI tool. And I'll talk a little bit about that. But some of the key pieces that go into that are developing hydrologic response units. Those are sort of the modeling building blocks. We used some high resolution data and the sampling points where Dan and his team had been doing sampling to delineate watersheds. And then we modeled our the area within the watershed to get those runoff and pollutant loading hotspots. So we'll cover those key pieces. Next slide. A brief overview of the OPTI tool. The OPTI tool is it's a regionally calibrated spreadsheet-based optimization tool for best management practices, BMPs, that EPA put together to help municipalities do these planning level analyses to look at where their stormwater pollution was coming from and optimize how they could treat it with different BMPs. And then this is, it's a spreadsheet based, but it uses EPA's sustain model, which is a really powerful optimization software for BMP selection. Next, please. And there's a link to the OptiTool on EPA's website. So kind of as a graphical overview of some of the processes that go into OptiTool and the pieces that we used for this project, it's driven by the watershed characteristics. So we look at, different GIS layers and put together the key physical attributes that contribute to water quality and runoff. And we drive that response of, rainfall being converted into runoff with local climate data. So this came from the New Bedford Airport, just precipitation and temperature. Those two pieces go into, there's a SWIM model, a stormwater management model associated with the OptiTool. And when you use those pieces in the model, you can get out runoff and pollutant loading time series. Next, please, Leah. Okay, go ahead and click one more. And those time series give you, over a long-term simulation, you can get sort of the hot spots of where these pollutants and loads are coming from. When we couple that with the catchment delineation, which I'll talk about too, you can then, especially help to pinpoint areas to farther investigate. Next. There are a few additional OptiTool processes that people can use, but we didn't use here. So, looking at BMPs and using it as an optimization tool to help pick BMPs. Next, please. Okay, so briefly about HRUs. So these are all, for the watershed, we get available GIS data. It's mostly things like land use, land cover, and soil type. And those are sort of the key pieces that drive runoff and water quality. So we, overlay all those in GIS and we look at the unique combinations and we boil it all down into categories that are that fit with what OptiTool simulates. Next, please. So this is, just a map of the final HRU categories that we had for the watershed. So there were 24 in all. We had 9 different impervious categories, 14 pervious categories. So things like forest, agriculture, it could be developed open space, sort of like lawns and things, and one to represent water. And throughout the watershed, there was about 27% impervious, roughly equal amount of forest, and then some developed open space, wetlands. And one key piece that, that we learned from this is the soil distribution, which is important for infiltration and being able to use BMPs that focus on infiltration. So the watershed is predominantly C and D type soils, which are usually lower infiltration rates. And so that, becomes a consideration in the designs of BMPs. Okay, so with our HRUs, we moved to delineating catchments within the watershed so that we could help pinpoint those areas for Dan to look at. So this was based on a high resolution digital elevation model from MassGIS, and as well as the stormwater pipe network, so that we could capture those parts of the watershed where the stormwater network was influencing drainage. So Dan had provided us these different outfall points that they were monitoring. And so we delineated a catchment for each of those points. That's this map, this first map on the left. And so with that gives us, sort of the rough estimate. We kind of grouped those into drainage clusters based on data that Dan had provided. And if we go to the next slide, we were able then to give that to Dan, and he went out with his team and did a lot of GIS and field verification of these drainage areas, to say, oh, the divide is on this side of the road or this side of the road, that sort of thing. And so he was really able to pinpoint and get good delineations for these 15 subwatersheds. And so we took that and we put it back into, using our HRUs, we can now look at the area loading for the watershed and for each of the catchments. So if you click one more, please, Leah. So this is the piece where, we're going to look at our time series. And again, these represent the unattenuated direct stormwater runoff. So that, we do this long-term simulation with our HRUs and the local climate data from New Bedford Airport. And that gives us a time series of what's running off of each different type of land surface and the pollutants associated with that. And so, within the OptiTool framework, that's really useful for planning and prioritization of sites. And you can compare relative contributions of stormwater runoff and pollutants for different source areas. Next, please. So we won't have to look at this one too long, but this is just kind of the summary of, when we look at like a per unit acre of each of our different hydrologic response units, what's the flow associated with that, or what's the different pollutants? So we looked at total phosphorus, total nitrogen, total sediments, TSS, and E. coli as some measure of sort of fecal indicator bacteria. And of course, what the literature has said about all of those is, generally the impervious and more developed have more of the pollutant loading. And so that's reflected here in the higher numbers for the impervious areas, with some exceptions, right? So agriculture will have, maybe nitrogen or E. coli, that sort of thing. Next, please, Leah. So with those unit area values for our HRUs, we can look at hotspots across the watershed. And I just picked out a couple pollutants to look at here, but the big driver, right, is the runoff, because that's what carries the pollutants. And so, looking at this graph, the top here is showing us the sort of the area normalized value. And so that's the rate, right? So for, say, a commercial area, all these impervious areas have, a relatively high rate of runoff because they're impervious cover. But in terms of the total for the watershed, that HRU may represent a smaller portion of the watershed. And so the actual total load from that may be, more or less depending on how much area it has. So we can see that from this, there's a lot of runoff from low density residential, roadways, highway, and then of course forest was a big percentage of the watershed, and so that has a good amount of runoff too. On the right is our map. So this gives us sort of the hot spot, the way to look in GIS and zoom into different areas and look at the areas where most of the runoff is being produced. And so, unsurprisingly, that's of course the impervious areas. But this will, generally track with each of the pollutants as well. Next, please, Leah. Okay, so we looked at the watershed, and then we can look at the different catchments that were delineated and do the same thing. So we can, sum up the total stormwater runoff for each of the catchments. We can look at their impervious cover versus pervious cover. And with this, right, you can, start to see on the map where more of that runoff is being generated. And so that, you can start to target those particular catchments. Next slide, please. Okay, so one pollutant to look at, we have, we weren't gonna show all the pollutants, but wanted to look at total nitrogen. Dan will talk about this more, I think, but this was, an important one for Buttonwood Brook. And so again, on an area normalized basis, so that's this top plot, all of our industrial, commercial, the impervious covers, residential, highway, those have the higher rates of nitrogen runoff. But we can also see that, as a total throughout the watershed, low density residential is giving us the most. But then there's also, besides roadways, the commercial, and then, developed pervious areas. So, lawns and those sorts of places as well. And a similar story, when we look by subwatershed, now we can look at the totals and see for any given subwatershed that we delineated, what was the total average annual nitrogen load. And so, you can look and see like, okay, Bliss Corner, that one was really high. Route 6, north and south, those were kind of in the middle. You can start to look at prioritizing these in terms of where you want to look at planning BMPs for mitigation. Just kind of as a summary, right? So this was a portion of sort of the OptiTool workflow. And so what we did was, we made those hydrologic response units, put them through the OptiTool swim model that gets us the loads and the runoff. And when we couple that with the delineation of the subwatersheds that Dan helped to do field verification for, that gets us closer to pinpointing areas to plan BMPs for future site analysis. Thanks, Leah.
So I just want to share a reminder that if anybody has any questions as we're going through, you can put them in the Q&A box on your Zoom menu on the bottom of your screen. Just a quick reminder, I haven't seen any come in yet. But so now I'm going to talk a little bit about the site prioritization. So taking the results of that mapping and modeling, some of the other considerations that we also looped into this in order to actually prioritize, okay, which stormwater projects do we want to go with? So Dan had a list, I believe, of like 75 different potential sites and projects that he identified for potential sites where various different types of stormwater management projects could be implemented. So how do you go from a list of 75 sites to kind of figure out, okay, which ones can we feasibly and realistically do, and which ones should we prioritize working on now versus later? So Dan and I worked really closely on this task to kind of identify what are the priorities for this project, and then how to translate that into a framework, a decision-making framework for prioritizing projects. So you can go to the next slide, Leah. I wanted to, at first, I'm not really going to talk about this, but I just wanted to kind of put this out there that this analysis looked at both sites, but also stormwater control measures, or SCMs, or you might also know them as BMPs, or best management practices. So just wanted to make sure everyone's on the same page that when we talk about SCMs or BMPs, we're talking about installed structures or systems that capture stormwater and remove pollutants from stormwater before it enters into the final waterway or into the ground or wherever that stormwater is running off into. So things like detention ponds, bioretention basins, permeable pavement, gravel wetlands, rain gardens. There are a ton of different types of measures or projects that you can implement. They come in many different types, many different sizes, like pretty much any site you can find an SCM that will fit your site, hopefully. And I would say, maybe not everyone, but I would, there's a lot of different options. And I would encourage you, if you're embarking on a process like this and you want to learn more about what your options are or how to pick the right type of SCM or BMP for your site and for your project and that fits your goals and your needs. The SNEP Network's Stormwater Retrofit Manual is a really great resource. So the link to that is in here and you can find out more there. But so that was kind of, that wasn't really part of this analysis. Dan identified the sites and the implementation projects, the SCMs. And then this work really focused on how to identify the benefits that would be provided by the different types of projects and how to prioritize which ones would be a better fit for the community. So you can go to the next slide, Leah. The first thing that we wanted to look at was site suitability. So you might have a great project, but if it's not really going to work on your site, then maybe like some sites are just easier to work with and some sites are more difficult to work with. So kind of the first step when you're looking at a project is what can the site handle and will it be able to handle the type of project that I want to install here. So some of the considerations that we looked at that we identified for this and are outlined in the tool that I'll talk about in a bit is the topography of the site and how water flows through the site or the hydrology. So how is the slope? You want a little bit of slope because you want to use that gravity to your advantage to direct water. But if the slope is too steep, then it might be really difficult to manage that flow of water without seeing issues like erosion. So you want some slope, but not too much slope. Soils are really important because that'll determine what type of SCM or BMP you can use. If you're going to be infiltrating the water into the ground, or if it's more about treating it and then piping it elsewhere. Other site considerations are what's underground. Is there bedrock underneath? Can you install, like, how much depth do you have for an installation? Also, what's the groundwater situation? And what is that groundwater feeding? Like if the site is on an aquifer, sensitive aquifer area, or next to a well area for someone's drinking water, then obviously those are going to influence what you can do on that site. And then just generally, what is the area available on your site? Ownership is a big one. If depending on who is doing the project, in most cases it's a municipality or maybe a nonprofit. Obviously, if the entity doing the project owns the site, there's no issue there. But if you don't own the site that you're trying to install a project on, you want to make sure that you have a willing partner who's going to be willing to work with you. So that can rule out a lot of sites just right off the bat. unfortunately. And then other general things, like we talked about groundwater, are there underground utilities on the site? And then some regulatory things to think about, like what does the zoning allow? Or is there other types of infrastructure on the site that you should be aware of? Next slide, please. So after thinking about sites, next we kind of thought about, okay, what about project feasibility and how compatible the project is for the site in question. So like I mentioned, all those site considerations we just talked about can limit what you can and can't do on a site. If the site is very limiting, that you can't really do the desired type of SCM, then that might be a challenge and make it more difficult. And then you also want to make sure that whatever you're doing on the site is not going to interfere with other existing uses on the site. Like if it's a park or a public area, you want to make sure you're not going to be impacting those types of access and uses. And then project costs associated with installing the project. One thing to think about is if site work is planned for a project, like if, say, your city is doing repairs on some street infrastructure or building a new park, can you take advantage of projects like that to install these types of projects while that other work is happening? Because that will save you a lot of time and money. And then you want to think about maintenance as well. So every stormwater control measure comes with its own maintenance needs, and that is outlined in that stormwater retrofit manual. So that's a big consideration for what you install, but you want to make sure that that's not going to be burdensome. And does the site allow the access that you need to do that type of maintenance? So that's something you want to think about when you're prioritizing sites. Next slide, please. So lastly, we also wanted to look at, these are kind of like the technical feasible, what makes a project possible or difficult or challenging. But we also wanted to look at the benefits that were provided by different projects. So most obviously the water quality. So the mapping and the modeling that Paradigm did was really helpful at identifying which drainage areas were contributing more to pollution in the brook. So that got factored into the prioritization that we did. But we also wanted to look at what other types of benefits we could get from these projects. And one way to go about that is incorporating green infrastructure into stormwater projects. If you can incorporate nature and natural solutions into your stormwater management practices, they provide a whole lot of co-benefits as opposed to some of the more traditional, like a paved swale or just kind of piping the infrastructure somewhere. If you can work in vegetation, trees, nature, you're providing a whole host of other benefits that is not only serving the same function of catching and directing that stormwater, but it can do a lot more in terms of treating the stormwater, filtering out pollutants, provide habitat for pollinators, birds, other wildlife, especially in urbanized areas like the watershed that we were working in, Buttonwood Brook. So we were a big priority of the project was to see where these types of projects might be able to offer green space and other habitat benefits in areas that otherwise maybe were lacking green space. Other benefits too are the cooling benefits offered by green space and trees, especially, that help to kind of offset some of the heat island effect. And protecting communities from storms, flooding, things like that. So we were trying to capture, prioritize projects that would also provide these other types of benefits. So next slide, please. So these are the considerations we looked at for the co-benefits. Again, water quality was a big priority. So looking at, with the mapping, if the site was located within one of those identified hotspot areas, and how well the project would address the pollutants of concern in Buttonwood Brook. Does the site and the project have potential to provide wildlife habitat, increase groundwater recharge, especially in these highly impervious developed areas, and then restoring habitat and wetland. That was another priority for the project. And then lastly, those climate resiliency and community co-benefits that we talked about on the previous slide. And we also looked at EJ communities, or if you don't have EJ areas, maybe other types of priority communities that have an unequal distribution of green space in this natural or green infrastructure. How can we prioritize getting more green space in areas that need it most? So those were those considerations. And then next slide, we took all of that, each of those categories, and put them into an Excel-based tool. So the link is here on the slide, and I think Leah's going to put it in the chat too, but on the SNEP Network resources page, you can access the slides from this presentation, the tool that we developed to do this site ranking, and a case study that kind of documents the process we went through for this project. So the tool, like I said, it's Excel-based. And it includes guidance on how to score for each category. It's all of the categories that we just spoke about. And it calculates, you put in the numbers for each site, and then it just kind of auto calculates, and you can customize it if you want to prioritize habitat over water quality, or if you want to really prioritize the climate resilience and co-benefits, you can change the scoring, maybe add a multiplier to the categories that you were most interested in prioritizing. So it is customizable, and you can kind of use it to your advantage however you like it. But we tried to design it in a way that it could be applied to other projects. So that's it for that. Next slide. I wanted to touch very quickly on some of the data that we use to do the prioritization that you want to make sure you have. A lot of these are GIS data, so it helps if you have GIS, or I apologize because this is for Massachusetts only, but if you're in Massachusetts, you can use the state's Mass Mapper tool, which has all of these data sets. But you want to, so just considerations for before you get started, how you might want to go about finding this information about these sites, and to be able to inform the ranking. And I think that's all for me. And I'll pass it back to Dan.
All right, thanks, Danica. Yeah, that was a huge undertaking to put that site matrix together, and I'd say it went through multiple iterations, not only just sort of in refinement, but also once we had all the sites in there and we started scoring them, the scoring process went through multiple iterations before we sort of were happy with where things were falling out, and what the categories were. So it was a great experience. And I mean, there was a lot of work that went into that, and it was extremely helpful in enabling us to engage stakeholders and get these sites prioritized. All right, Leah, next slide. So, I mean, we're kind of backtracking a little bit here, but I'll just give you a little bit of an overview of, how this project went forward. When we started, we established water sampling sites up and down the brook. It's a small stream, but it's also a complicated stream with 9 miles of stream channel, multiple tributaries flowing through a really urbanized area with extensive stormwater networks and upwards of 60 stormwater outfalls discharging to the brook from surrounding areas. So we established testing sites. It was an adaptive testing program. Over time, as we started to see results, and we wanted to bracket in to more localized pollution sources, we added sites, moved sites. We also deployed data loggers up and down the brook to measure water level. And then alongside those water level loggers, we conducted flow measurements to get discharge rates in cubic meters per second. So we could see how weather events were impacting flow in the brook. And then we contracted an environmental consultant to do habitat assessments up and down the brook. And in partnership with our main engineering consultant, we did some dimensional analysis in the stream at about 40 different sites to measure sort of the trapezoidal channel shape, bankful depths, flood-prone areas alongside the brook, so we could get an idea of where the brook had healthy structure and shape and where it had unhealthy or highly modified shape with sort of urban stream syndrome symptoms of bank collapse, incision, cut off from its surrounding floodplains. And that really started to, narrow us into some areas. And then I would say about 2/3 of the way through this process is when we went to Khalid and Ben, and we started looking at doing the pollutant load modeling. And I think that analysis that you saw in Ben's brief just really layered on top of all this other stuff we were doing. And it was really helpful to complement and validate or unvalidate some of the stuff we were looking at in the brook and help us look at specific areas. And then downstream in the bay, we also had sensors deployed so that we could look at and interpret the interaction between the freshwater inputs to the bay and what was happening in the bay with water quality and parameters like dissolved oxygen that are a good indicator of water quality in the bay. So a lot of data collection in the watershed to combine with the pollutant loading analysis and help us to feed into the site prioritization. Next slide. And so here's sort of the end process that we ended up using with our engineering consultant. And the whole purpose of this was to sort of get us down to 10 sites. And our plan was to actually have the consultant go forward with concept designs for 10 sites, the top 10 sites as they fell out from all these different criteria. Which includes a lot of stakeholder input and, a live survey that we did during one of our meetings, and then be able to further reduce those 10 sites down to 3 or 4 that we would actually implement under the grant program. And you can see on the left-hand side here, there's a lot of data that we, including the pollutant load modeling study that we gave to our consultant. What they did is they went through all of that, incorporated the dimensional analysis, and then came out with a matrix of 10 sites. And that, again, that matrix was not a single iteration. There was a lot of back and forth on that group of sites until we finally came to 10 sites that we all agreed upon would bring the greatest benefit to the community. And really, we were looking, in the upper right-hand side of that slide, we were really looking for this nexus of, what sites bring water quality, resilience, habitat, and, the one circle missing there is benefit to disadvantaged communities. And then cost benefit analysis on those sites to sort of look at what's the cost per pound to remove nitrogen. And that was really a big determining factor in what we went forward with, and some green infrastructure or nature-based solutions can produce a lot of nitrogen removal at a lower cost than others, which, something like a dam removal produces a lot of benefits in addition to water quality. But it's also very expensive. So we had to balance all those things out as we went forward and looked at what sites we were going to finally adopt. Next slide. So, we finally came down to a matrix of 10 sites. We held multiple stakeholder meetings. Stakeholders voted on those sites. We did the cost benefit analysis of cost to remove bacteria and nitrogen per site. And then we finally settled on a few final projects. You know, the other sites that didn't make that final cut are still on our radar screen, and we would like to go after those in, you know, future iterations or in the future, or maybe the municipalities will end up, you know, trying to address those sources of pollution. But, you know, on the right-hand side there, you sort of see the Buttonwood watershed with the headwaters of Buttonwood Brook at the top. The watershed's outlined in blue, and then the receiving waters at Apponeganset Bay down at the bottom. And those yellow dots are sort of where we are currently either in planning or getting ready to implement either stormwater control measures, ecological restoration, or potentially, you know, an incentive program to get people with access to sewer, but who continue to operate on-site septic systems to connect their homes to sewer. You know, what we found after doing some additional analysis, and, you know, Ben and Khalid's pollutant load modeling, you know, showed us what piece of the wheel that stormwater was contributing. But then we had this whole other empty piece of the wheel, and with the help of Joe Costa over at the Buzzards Bay National Estuary Program, we were able to sort of quantify the number of septic systems inside the watershed and then calculate an estimated load that those were producing, and then look at, you know, potential ways to help incentivize connection. And really that turns out to be one of our most cost-effective ways to reduce nitrogen in the bay. But I'll just quickly run through these projects. So up at the top here, we've got the Kempton Corridor, Route 6, as it runs through New Bedford north of Buttonwood Park. This is a huge impervious area, about 1.5 million square feet of impervious, all drain directly to Buttonwood Brook untreated. And not only was it putting a lot of nutrients, bacteria, and sediment into the brook, it was also creating these huge peak flows that were, you know, impacting the brook structure, causing a lot of stream bank, a lot of incision. So this was a priority. We ended up partnering with the city of New Bedford. Buzzards Bay National Estuary Program partnered on this project. And what was initially a $325,000 MVP project became a $3.7 million green infrastructure nature-based solution project with 24 BMP sites and a variety of funding sources brought to the table to try and reduce pollution there. Down below that is the Buttonwood Pond. That was, you know, really the first open body of water to receive all that pollution. But also it's held up by an 1800s era dam that's a real public safety risk. And our second project is a plan to work with the city to remove that dam spillway, create a free-flowing system, and then restore that residual impoundment to natural wetland that can flood and drain and improve community resilience while also improving water quality and community experience around that dam, around that former impoundment. You know, moving immediately south from that is the Buttonwood Zoo. This is a site with legacy stormwater infrastructure, 28 stormwater catch basins inside the zoo with 13 stormwater outfalls that drain directly to the brook. Many of those catch basins are either adjacent to or inside animal enclosures. So there's a huge bacterial loading issue coming out of Buttonwood Zoo. Buttonwood Zoo and the city of New Bedford have been amazing partners on this project, have given us all access. We've been able to map that infrastructure, which was previously unmapped, and then worked with our consultant to develop some concept designs that we're hoping to move through permit level design, final design, and construction in the next couple of years that will mitigate a lot of that bacterial pollution coming out of the zoo and produce some aesthetic improvements inside the zoo that I think will benefit the community. So these top three sites are really addressing some of the largest sources of nitrogen, phosphorus, sediments, and bacteria in the entire watershed. And they're also being done in areas that are going to really directly benefit underserved and environmental justice communities that were bearing the brunt of the pollutant load coming out of these areas. And then as we move further south in the watershed, the other project site that we opted to go forward with was a series of 2 dams and poorly designed culverts in the lower watershed. These dams are legacy dams. They currently serve no purpose. They're not flood controlled. They're not generating power. They're associated with old mill infrastructure from the 17 and 1800s. And they are, along with the culverts, they are creating some resilience risk for the community with flooding, and they're also an impediment to fish passage and aquatic connectivity on the brook, both up and down the brook. They're inhibiting migratory fish passage heading upstream, and then they're disrupting sediment transport going downstream. All the sediment that would normally come down through there is crucial to the salt marshes that are in Apponequet Bay. So this project will look to modify both of these dams to remove the dam walls or spillways and create a free-flowing system. Those impoundments that were essentially fluxing nitrogen and bad for water quality are going to be converted into wetland, and then floodplains adjacent to these dams will be reconnected so that we have additional flood storage and increased community resilience in these areas. And then those are really the lowest areas on the brook. So, a sort of a collection of projects that, weren't necessarily the top 4 on the list. But as we started to do deeper analysis and engage stakeholders and look at all the different feasibility aspects that were teased out through the prioritization matrix and the pollutant loading and all of our testing, we were sort of driven into these 4 areas as our initial attempt to improve water quality, resilience, habitat in this watershed. Some of our big takeaways that, looking at a whole watershed, doing a watershed scale analysis and trying to just pick projects is a really difficult task. And the work that Khalid, Ben, and Danica did for us was extremely helpful to put things into context and at least give us a process to start looking at this through, so that when we went to the stakeholders, we had a process to pull them into and to get them engaged. And that is one of the most important parts of this entire community-based effort, is to have a process that you can point to that quantifies why you're looking at certain sites and why you're not looking at others. There's a lot of equities and a lot of criteria with all the different voices out there and all the different variables that can be applied to each site. And these were really helpful. I think I mentioned this before, but the loading analysis really was an amazing thing to pair up with all the water quality data that we had, and it gave us sort of a visual representation of where some of the heaviest loading was coming from. I would say that EPA's pollutant load export rates, there's still some holes that didn't let the model really fully maximize its potential. And this is a unique watershed, but the zoo is one thing that Khalid and Ben just weren't able to model in the broader analysis, because there's just no pollutant load export rate for an urban zoo. And that actually sort of spurred us to go take a closer look at the zoo and partner with Buzzards Bay NEP to go in and map that infrastructure and do bacterial testing at every single one of the 13 outfalls in the zoo. And then do that in wet and dry weather. And that sort of allowed us to really focus in on the 3 subcatchments within the zoo that were producing the highest bacterial loads. So in a lot of ways, there's gaps in the model, but those gaps also sort of keyed us into areas that we needed to get in on the ground and dig deeper on. So a lot of good synergy there. And I think I've covered this one already. In this particular watershed, just like most watersheds and stream systems, they cross municipal boundaries. And there's sort of this tendency to want to, defer acting in your portion of the watershed because, maybe there's an anecdotal belief that the pollution's coming from the other side, and that they're the ones who should solve the problem. So, you know, the pollutant load modeling was shared with the municipalities, and I think it was a real wake-up call for them to see that the pollution isn't coming from one side or the other, that it's actually widely distributed, and that this is a shared problem. And it helped us bring them to the table and increase just productive communication between the municipalities, which I thought was great. And it also, you know, having all this data allowed us to fuel additional grant applications and motivate the municipalities and the communities to want to take action. When you see these shaded maps and you see this prioritization matrix, a problem that really can seem quite overwhelming, and that you just want to sort of kick down the road, suddenly starts to seem like it's solvable. And you know, having this stuff was really a game changer, I think, for the desire to take action and the feeling that something could be done about this. This is a solvable problem. And then, you know, finally, I think, you know, we identified that, you know, EPA's got some gaps in their pollutant load export rates, but also that the EPA loading rates for nitrogen still sort of remain a little bit high. And because, like I discussed earlier, this project also has a TMDL as its goal, so that we can get that in place and sustain the water quality gains we make. We didn't want to overweight stormwater in the broader equation of what's bringing pollution to the bay. So we sort of, you know, had to fall back and look at, you know, some alternative loading rates. It didn't influence how subcatchments were ranked because it's all relative. So the pollutant load modeling still focused us in on the right areas. It was just for us looking at this from a TMDL perspective, we had to sort of fall back and make sure the way we presented it to the community and to the regulatory agencies was that nitrogen loading in the EPA published numbers is probably overstating the contribution stormwater makes, and that those numbers are only representing unattenuated nitrogen loading on site and not what's actually emerging down at the mouth of the stream as it passes through, you know, parts of forest that still have connected floodplain and wetlands and other, you know, natural features that do a great job of pulling nitrogen out of the water. So, you know, overall, this was a great experience, and I'm really thankful to everyone who contributed to our project in this way. I think that was the last slide.
Yeah, and we do have a question for you, Dan, in the chat. Are there any plans to continue monitoring water quality after implementing the BMPs to compare with the initial monitoring results?
Yeah, that's a great question. So when EPA first designed this pilot watershed grant, they built post-construction monitoring into their budget. It doesn't come out of our budget. Our $750,000 budget isn't paying for that monitoring, but EPA is separately contracted with you know, an environmental consultant to conduct monitoring. We've been working with them over the last year or so to transfer all of our water quality sampling and data logger and the pollutant load modeling data. We've basically given them everything that we've looked at in the watershed, and they are right now, as well as our implementation sites, and they are right now sort of crafting a multi-year monitoring plan that'll be implemented, you know, under EPA guidance that'll go on for several years. So I feel like, and then in some of the projects like our Kempton Street project, we actually built a 6-month post-construction monitoring plan into that SNEP watershed implementation grant that we're going to do on our own because we want to be able to work with the city and gain some immediate lessons learned from the Kempton Street project so that we can transfer those lessons learned to other areas in the city. the city of New Bedford has a expansive green infrastructure implementation strategy. And I think Kempton being sort of the kickoff project of that strategy, we wanted to make sure that we capitalized on lessons learned from that project so the city can go forward on its others with armed with those lessons learned.
Well, I am not seeing any other questions, and we are at time, but Leah is putting links to all of these materials in the chat if anybody wants to open those links before you hop off. But I think we'll end there. Thanks, everyone.
Yeah, thanks, guys.
Thank you all.
Thanks.
Have a good rest of your day.